Okay, pairwise comparisons. Through the two main effects being significant, we conclude that, conclusions, one, controlling for the species body mass is different between males and females. That's our first main effect. Two, controlling for the sex body mass is different for at least one species. That's our second main effect. If body mass is different between the two sexes, given that there are exactly two sexes, it must be because body mass is significantly different between females and males, right? But if we want to know which sex has the highest body mass, it can be deduced from the means and or box plots by subgroup. That's pretty easy, right? It's clear that males have a significantly higher body mass than females, just looking at the plots and looking at the means. However, it's not so straightforward for the species. That's because there are three species, Adelie, chinstrap, and gentoo, so there are three pairs of species to compare. Our three species to compare are Adelie and chinstrap, Adelie and gentoo, and chinstrap and gentoo, right? That's three separate comparisons. And the same as for a one-way ANOVA, we cannot at this stage know precisely which species is different from which one in terms of body mass. To know this, we need to compare each species by two thanks to post hoc tests, also known as pairwise comparisons. So there are several post hoc tests, the most common ones being the Tukey HSD, which tests all possible pairs of groups, and the Dunnett's test, which compares all groups to a reference group. As mentioned earlier, these tests should not be done on the sex variable because there are only two levels. In this lab, we will only do the Tukey HSD test. As for the one-way ANOVA, the Tukey HSD test can be done in R as follows, and we've done this before, right? Tukey HSD is our function, which we run on the model where we store the results, and we say which equals species, because we only want to compare the species, not the sex. And now we can see this handy little table, which shows us that the mean of chinstrap minus the mean of Adelie is 26.92385 grams, right? That's the difference between the two of them. Right away, which one is bigger? What do we know? Which one's bigger? Well, chinstrap's bigger. Besides that, we looked at the plots and we could see that chinstrap was bigger. Remember that was the one with the little line. That's positive. So chinstrap minus Adelie is positive. If chinstrap were smaller, then chinstrap minus Adelie would be negative. So if the difference is positive, then this first species is larger. And the difference is 26. Is that a very big difference? 26 grams? No, that's a pretty small difference. That's pretty light. The lower confidence interval, that's what this lower is. That's the confidence interval. The lower confidence interval for that difference, remember, we never really know exactly what the difference is, but we can say it's probably plus or minus this much. Like it's somewhere here, plus or minus this. That lower level, that minus, is negative 80. So it might be that it's negative 80 difference, which of course doesn't make any sense because there's no such thing as a negative 80 difference. Well, right. Okay. Yeah. It could be that chinstrap is actually smaller. Then it would be negative, right? And the upper confidence interval is 133, right? So it could be more. Now, imagine these two numbers on a number line. Picture your number line in your head and go from negative 80 to 133. Is zero somewhere in between there? Is zero somewhere on that number line in between there? Yes, zero is somewhere between negative 80 and 133. One of those numbers is negative, one of them is positive, zero is in between. That means that the difference could also be zero. The confidence interval contains zero. Remember, our null hypothesis is that the difference in means is zero. Right? The null hypothesis is that the difference is zero. They are equal. One mean minus another equals zero. And that number zero is somewhere in those confidence intervals. So we can't rule it out. We can't rule out that the mean difference is actually zero. That's why we see that the p-value is 0.82. The p-value is greater than 0.05. We do not reject the null hypothesis of no difference in means between these two species, right? Breaking it down. Now let's look at the next two species. Gen 2 minus Adelie. So if you take the mean of Gen 2 and you subtract the mean for Adelie, remember this is males and females grouped together, just comparing Gen 2 and Adelie, the difference between them is about 100 or 1,377. 1,377. That's a much bigger difference, right? The lower confidence interval for that is about 12,087, and the upper confidence interval is about 1,467. Now, again, if you picture these numbers on a number line, you picture 1,287 going up to 1,467. Is zero somewhere in between those two numbers? No. Zero is like not between those two numbers, it's way over there. So the mean difference is not zero. We have pretty good estimate, pretty good confidence. You could say we're 95% confident. I mean, that doesn't really make sense, but you could say that we're 95% confident, you know. It's not about how we feel. It's not our emotional state. It's the math. Within the 95% confidence interval, we can safely state that the difference between the mean weight of Gen 2 and Adelie is not zero. Therefore, we reject that null hypothesis. You're out of here. Look at that. P-value, much smaller than 0.05. It's not zero exactly. It's just less than 0.00000001. It's pretty small. So we know, okay, there's a difference. There's a significant difference. Next, Gen 2 to chin strap. So if you take the mean of Gen 2, the mean body mass of Gen 2, and you subtract the mean body mass of chin strap, the difference between those two means is about 1,350. Again, that's a pretty good amount, right? Grams, so that's like 1.3 kilos, which is, you know, a few pounds. So what do we get here? The lower confidence interval is 1,239. The upper confidence interval is 1,461. Imagine these numbers on a number line. Is zero somewhere between 1,239 and 1,461? No, it's not. It's outside that confidence interval. So the idea that it would be zero difference or that the means would be equal is outside of our estimated range, right? Which means, again, we reject the null hypothesis. We have a very small p-value. We have a very small p-value. So this is how it all works together. That mean difference, the confidence interval, the p-value. We can say, yes, there is a significant difference in mean body mass between Gen 2 and chin strap. In other words, we can say, look, Gen 2 is bigger than Adelie, right? These are all positive differences. Gen 2 is bigger than Adelie. Gen 2 is bigger than chin strap, but chin strap and Adelie are not different from each other. Okay, great. We've got it. Now we have our comparisons. I'm going to walk you through a bunch of other ways of looking at those comparisons that I think might make it easier. See what you like. This does the trick. This does the trick. You just run that Tukey's test on the model, decide which factor you want to look at. There you go. Now we could try using this mult-comp package. And the mult-comp package gives us a little bit more stuff, some more bells and whistles here. So if we run this chunk, what we're going to see is we're going to look at, we're going to basically put that model in again without the interaction term, and then get the summary. And we're going to look at the simultaneous test for general linear hypotheses. And this basically gives us the same thing. It gives us the same thing. And again, it's taking into account the fact that we're doing multiple comparisons, and it's adjusting our p-value for us automatically. Now, what this is doing here is it's saying, if our linear hypothesis, it's like restating our hypothesis for us in case we had forgotten, is that the difference between chin strap and Adelie is equal to 0, right? What's the actual difference? 26. That's our estimated difference. The standard error of that difference is 46. The t-value of that difference is 0.579, and the p-value is 0.83. So it's kind of like it ran a little t-test on just these two groups and said, here's our estimated difference, here's the standard error of that difference, here's the t-value, here's the p-value, same result. There's no difference between Chinstrap and Adelie. We reject the null hypothesis, or we fail to reject the null hypothesis that the difference between these two means is 0. The difference between these two means is possibly 0. There's no difference. Okay. And then for Adelie and Gen 2, same thing. We're testing the hypothesis that the mean difference is equal to 0, and we reject that. Same thing for Gen 2 and Chinstrap, we reject that. The mean difference is not 0. It's something different than that. Okay, so there's another way of looking at those pairwise comparisons. A third way, method 3, using the pairwise t-test function, and you can actually use different methods for adjusting the p-value, because again, the p-value has to be adjusted for multiple comparisons, and these tests do it for you automatically. And there are different ways of doing it. And this one, this code allows you to change that method. Here we're using the BH method, which I think is the Bonferroni comparison. You can use different ones depending on what's appropriate for your data. Run that chunk and you see we get a sort of different way of looking at it. I don't really like this one as much. It's more like a crosswise table, but comparing Adelie with Chinstrap, our p-value just gives you the p-value is greater than 0.05. So you're like, okay, there's no difference between those two. But when you compare Gen 2 and Adelie and Chinstrap, you see there's a difference. This just gives you your p-value. I kind of like the ones that actually also give you the mean difference. You know, the first one gives us also the mean difference. The second one gave us the most information so far because it gave us, well, it didn't give us the confidence intervals, but it gave us the standard error of the difference and the t-value. Yeah. What do you want? What do you want? Different ways of getting it. Okay, so yeah, and just note that with the second method, you use the model without the interaction. Even if the interaction is significant, that's what you have to put into that function. But all of these methods give the same result. So body mass is not different between Chinstrap and Adelie. The p-value is 0.83. And body mass is different between Gen 2 and Adelie. The p-value is less than 0.001. And body mass is significantly different between Gen 2 and Chinstrap. Again, the p-value is 0.001. And, you know, it's nice to say that body mass is larger, or, you know, when you state your results, you have to put your mean differences and your confidence intervals or standard errors for me, right? Remember that it is the adjusted p-values that are reported to prevent the issue of multiple testing, which occurs when comparing several pairs of groups. If you would like to compare all combinations of groups, it can be done with the Tukey HSD function and specifying the interaction in the which argument, right? So now we run that Tukey HSD on our model, but the difference is we say which equals sex by species. And that's why I changed that model, so that in here I could have that sex by species as a term in the model. Otherwise, it wasn't showing up. So if we run this, now we get this big table, which is a lot more complicated and a lot more to look at. But breaking it down, you can see that what we have here is male Adelie compared to female Adelie, right? Is there a difference? If you took just the Adelie and you got the mean of the males and the means of the females, and you subtracted the mean for the female from the mean from the male for just that species, the difference in means would be about 674, right? And the lower 95% confidence interval would be 527. The upper 95% confidence interval would be about 821. And does that confidence interval include 0? It does not, right? That means we're 95% confidence interval. We can state, no, that mean difference is not 0. It's not 0. Reject the null hypothesis. And the p-value is less than 0.05, right? Reject the null hypothesis, the mean value is very unlikely to be 0. And if we look down here at the female chin strap, compare that to the female Adelaide. So now we're comparing females and females of two different species, right? The female chin strap and the female Adelaide. They're just the ladies here, but two different species. And if you subtract one mean from the other, the difference in means is 158. And the lower confidence interval is -25, and the upper confidence interval is 342. So does this confidence interval include 0? Yeah, it does. -25 to 342 includes 0 in there somewhere. And that means that mean difference between the female chin strap and the female Adelaide could actually be 0. It might be nothing. It might be not different, in which case the p-value would be, and here's what you have, greater than 0.05. You fail to reject the null hypothesis. You have to say there is no difference. There is no difference between female chin strap and female Adelaide mean body weight, right? And you could go through all of these in the same way, but I'm going to show you an easier way to look at it, because that's a lot. Just doing all these different comparisons. There's how many? There's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 different comparisons that you have to do for each pair. Okay, so I'm going to try doing it a little bit different now. I'm going to use the Agricole package to run the Tukey's test and do these multiple comparisons and print the results in a slightly different format. And this actually gives you a table which shows you female Adelaide, body mass, standard deviation, an R value, a standard error value, min, max, quartiles, all this stuff. It gives you a lot of information, a whole bunch of tables, and you can kind of toggle through them. So it really breaks down exactly what's going on for each subgroup of the 6 groups. And then what it does here, if you look at this last table, it says, okay, for male Gentoo, the body mass is 5,484, and its group is A. I don't know if you've ever seen this before in publications. Sometimes you see a graph, and above the dots or the bar, you'll see letters, A, B, C, D, etc. And what that is telling you is that if the groups match, then there's no difference. If they don't match, they are different. So again, male Gentoo is group A. Female Gentoo is group B. They're in different groups. That means there's a significant difference between the male Gentoo and the female Gentoo, right? They're not the same. Male Adelaide is a C. It's in the C group. That means it's different from A and B. It's different from the male Gentoo and the female Gentoo. But the male chin strap is a C also. So that means male Adelaide and male chin strap are not different from each other. They're in the same group, right? It sort of gives you that little handy way of telling which groups are different from the other. And then female chin strap and female Adelaide are both in the D group. So they're not different from each other, but they are different from everything in the C group. And they're different from the B group. And they're different from the A group. Hey, see how that works with the letters? Handy, right? Now, if you have a lot of groups to compare, it can be overwhelming. And sometimes it's easier to just put them onto a plot. And here's a way to do that. Now, the first thing I did here is I set this par function, which sets the margins of the plot so the labels didn't get cut off. You may or may not have to do that. You may just need to use this plot function, which we've used tons before, on this Tukey HSD, which is the function that does the Tukey's test for multiple comparisons. And you run that on the model, which is where you're storing the results of your model. And again, you say which, and you say sex by species. So you want to run it on the interaction terms, so you compare all 6 groups. LAS is just a graphical parameter function to rotate the x-axis ticks. And when I run that, I get this little plot here. And this is a really nice plot. It's a really nice plot. I know the labels on it can be like, oh, that's a lot of words, but you see what this is doing here. So each one of these little ticks here in the middle is the mean. And the error bars are the 95% confidence intervals. So it's just the same thing as what we saw up here. It's the same thing as in this table, except in a picture, which is easier to see, right? So we can see male Adelaide and female Adelaide. If you just compare males and females of the same species, are they different from each other? Well, do those confidence intervals overlap the 0 dashed line? No. So they're different, right? That p-value is going to be less than 0.05 then, right? Now we compare female chinstrap to female Adelaide. The mean difference is in the middle and the confidence intervals on the side. Do the confidence intervals overlap that 0 dashed line? Yes. So they're not different. They're not different. The female chinstrap is not different in body size between the female Adelaide. Male and female Adelaide, different? Yes. Female chinstrap, female Adelaide, different? No. Right? You can go through all of them. You can see, okay, this comparison, male chinstrap to female Adelaide, different, 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 different. Oh, not different. Male chinstrap to male Adelaide, not different, right? We have two comparisons that are not different. And basically what we're seeing is that we have the males and the females of the chinstrap and Adelaide don't differ from each other. All the girls of those two species are not different. And for the males of the chinstrap and Adelaide are not different, right? So if you had a group of species and you had chinstrap and Adelaide standing next to each other and they're both females, the size would be probably roughly the same. And if you had chinstrap and Adelaide standing next to each other and they're both males, the size would be roughly the same. Right? Now we can write our question 6 from the output and plots above. We conclude that all combination of sex and species are significantly different, except between, what's the comparison that was not different? What's the comparison that was not different? What I just told you, female chinstrap and female Adelaide, and the p-value you take from this up here. So except female chinstrap and female Adelaide, and the p-value is 0.13, right? So it's female chinstrap and female Adelaide point, right? So you put that in here. Down to the question between, so female chinstrap and female Adelaide, and the p-value, I'll just copy it, paste it into here. And then the other non-significant difference was the male chinstrap and male Adelaide, and the p-value for that was up in this table here, male chinstrap, male Adelaide, right? The p-value was 0.58. Come down to the question here and just fill in the blank there, right? That's it. That's your answer. So these results are in line with the box plots that we looked at above and will be confirmed with the visualizations below.